Finding the length of curves, or arc length, is something that you frequently have to do in many different applications. So for instance, if you're going on a trip, you might want to know how far you're planning to go or how far you've gone. For aircraft and for boats, commercial aircraft and commercial boats, there are systems in place to help track them, which is actually pretty useful for predicting when an airplane or a boat is going to arrive, if it's running late, or if it gets lost, help find it. These systems are in place all the time, and they can give you a pretty good idea of what's going on. So for instance, there are a number of websites that will display all the air traffic in your area. For instance, here in the greater DC area, you can see there's a whole bunch of airplanes moving around, and all of them are reporting back to a central station, and that's getting displayed. The system is called ADSB. It's not particularly important for calculus, but what is important is to understand how this might be used for finding the length of a trip. So for instance, if you happen to pick one flight, here's a flight. There's where the airplane is now. It started off at DCA, and it's going to MDW. Those are two airport codes. And the aircraft is moving along this path. It's gone part of the path, and it's going to go, it has a planned route for the rest of the path. Now, if you look inside this curve that the plane is flying along, it's broken up into a bunch of little points. Points with latitudes and longitudes, and between those latitudes and longitudes there are distances. Of course, the simple thing to do is to add up all those distances. That will tell you how far the flight is. So if we want to compute the length of the aircraft's flight, we just add up all the little pieces. Adding up all the little pieces sounds like an integral, and indeed it is. So the idea is, if I have my flight, it has a bunch of waypoints. On some flat grid, or more or less flat grid, that could be latitude and longitude. And you can imagine, to a rough approximation, that you have a whole bunch of linear segments, line segments, connecting them. And so what you'll do is you'll want to add up the length of each of these little segments. Say this is L1, L2, L3, L4, L5, and so on. So the total length is the sum of all of the various lengths. And how do you find the length of one of these line segments? Well, it's just the Pythagorean theorem. The change in x squared plus the change in y squared, quantity square root. And perhaps I should tag these with n's so that you know they can change. The change in x and the change in y can be different. Now, if all the change in x's are the same, I can rewrite this equation a little bit. So if I assume that all the changes in x's are the same, I can factor out that delta x. And then I'll have delta yn over delta x, quantity squared. You should notice right away that that square root of delta x squared is just delta x. And delta y over delta x squared is still under the square root sign. Well, as I take the number of segments to infinity, take the length of each little segment to 0, this thing should turn into an integral. An integral of dy dx, quantity squared, dx. And this is from the x start to x equals n, wherever that happens to be. Okay, this sort of thing is perhaps best done by example. So let's do that. Here's a pretty simple example, as let's find the length of a line segment. From x naught, y naught to x1, y1. Okay, in order to do that, we need an equation of the line. Okay, you could write that in a variety of forms. Let's just use point slope form. So I now need the slope. And you should notice if I put in x is equal to x1, I'll find out that y is equal to y1. If I put in that x is equal to x naught, I'll find out that y is equal to y naught. Just as a quick note, quantity here, this is the slope of the line. Okay, that's handy because I need a dy dx in there, a slope, and that's just going to be my slope. Okay, so moving right along, integral from x naught to x of square root 1 plus y naught plus x minus x naught, y1 minus y naught. Oh, whoops. I just need the slope here. My bad. My apologies. We just need the slope, and we're going to square it. Squared. Okay, dx. All right. Just rearranging the algebra slightly. But I haven't done any calculus, I've just rearranged the algebra. Now you will notice the quantity under the integral is a constant, so I can just take that out. And if I take that quantity out, and integrate from x naught to x1, well, what do we get? Well, there's the quantity out front. Let's integrate it from x naught to x1 dx. Notice the denominator is actually the square root of a square. And this is kind of like a Greek tragedy. You can kind of see the end before it happens, because the length of the line is actually in the numerator. And this second quantity, although it's written kind of in an elaborate way, is actually just what we need. To cancel out the denominator. And yes, indeed, this is the length of the line segment. So the formula appears to work. Um, Word of caution though, finding arc length, although it's fairly easy to write down the integral, can be rather difficult to evaluate the integral. So let me give you an example of an integral that is harder to evaluate and yet does the right thing. Let's find the length of this semicircular arc. Semicircle of radius 1. Looks like this. Okay, well, this is a semicircular arc. We already know what the length of a semicircle is. What's the length of a semicircle? Well, it's half the length of the circle. So this is 2 pi. R is 1 divided by 2, because I've got half of it. So this should be pi. Now, you look and you say square roots. You don't see pi's. You know there is trouble somewhere. So the arc length is, let's write the formula. I'm writing it in a very compressed way now so that you can see it in all of its various forms. One plus, now let's say, taking the derivative of this quantity. This is already looking a little troublesome, but it's not too bad. The derivative of an x squared, let's just use the chain rule to work through that. So this is 1/2 square root 1 minus x squared. That would be the outer part of the chain rule. The inner part of the chain rule says I should get a 2x in the numerator. And that whole thing needs to be squared. I think you can notice the two x's, the 2x and the x in the denominator cancels. So this is x squared over 1 minus x squared. Again, a little bit of algebra is useful. Just putting the two fractions on a common denominator. All right, and we get this integral. And you'll notice there's no pi's in sight. That, of course, means that there's something a little terrifying going on. The thing we need to use to fix this is actually a clever trick that is trigonometric substitution. And so what we actually want to substitute is not u equals something, but rather x equals something. This substitution turns out to do the job. And if you haven't seen it before, well, no time like the present. Okay, take the derivative of both sides and rewrite our integral. My limits now need to be in terms of u. These are inverse signs. The inverse sign of -1 is negative pi over 2. That's where the pi's come from. It's actually the limits. The dx becomes the du thing, but it's a cosine u. About the denominator, that's 1 minus sine u squared. And the Pythagorean identity comes to the rescue. Because this is cosine u squared, and I'm taking the square root of it. You'll notice cosine is positive on this whole interval from minus pi over 2 to pi over 2. So there's no problems with that. And so all of these trig functions vanish, and we're just left with pi. So indeed, we've recovered that length of a circle. Now this idea works for any sufficiently nice curve, one that you can take a derivative of, and that derivative turns out to be continuous, and then you're in good shape. So then you can find the arc length. It's typically the case that writing down the integral might be a little bit tricky. True enough. You might even get an integral you can't do, at least analytically, but maybe you can solve it numerically and come up with a good approximation.